Hey everyone, welcome back to another AP Precalc video. This is lesson 2.2. Let's get right into it. All right, so here's a bell ringer for today. Pause the video if you haven't done so yet, because I am about to go over the answer. So consecutive terms of a sequence have the values of 6, 2, -2, and then -6. I think there's a typo on your page. It should be -6 as the last term of the following, which describes the sequence. And so if we just take a look, it is pretty easy to identify that you are decreasing by the same amount each time. You are subtracting 4 to go from one term to the next. And so when you are adding or subtracting the same number to go from one term to the next one, that's an example of an arithmetic sequence. So we can eliminate C and D. Geometric would be if you're multiplying by the same number, which is not the case here. And then here there is a common difference. So difference is going to be part of an arithmetic sequence of -4. Ratio, common ratio would go with a geometric sequence. So we know the answer is A. Just by these two words here, B would never be correct or C would never be correct because a common difference will only go with an arithmetic sequence and a common ratio will only go with a geometric sequence. All right, so last time on AP Precalc, we learned that arithmetic sequences behave like linear functions and geometric sequences behave like exponential functions. So for example, if we have an arithmetic sequence like that, that's an example or very similar to a linear function. Or if you had a geometric sequence like that, that is very similar to an exponential function like that. And so we will explore the connections, the similarities, and differences today. And so here is the arithmetic sequences and linear functions. This is our general equation for an arithmetic sequence. Notice how that is so similar to linear functions in point-slope form, right? So kind of like y2 equals y1 plus m, x minus x1, or y equals y1 plus m, x minus x1. That's point-slope form. And so these two are almost the same, with our d kind of being the same thing as our slope for a linear function. The same thing with geometric sequences and exponential functions. Our general equation for a geometric sequence is seen there. And then this is our general equation for an exponential function, where it's f of x equals a times b to the power of x, or you could write this as a times r to the power of x, where in this case r and b are almost going to act as our same thing for geometric and exponential functions. All right, so talking about the similarities and differences, there'll be a multiple choice question on your next test, testing this. Same thing with your semester summative. There's another multiple choice testing this chart right here. So for linear functions, they're in the form of y, or f of x, equals mx plus b. That's just another way to write a linear line. That's slope-intercept form, where you can get your slope and your intercept rather quickly. For exponential functions, they're always going to be in the form of a times b to the power of x. We will learn more about that in 2.3. And then for linear functions, over equal length input value intervals, the output values change at a constant rate. That is kind of what we talked about way back when in 1.3, when you were given a table and you had to describe if it was linear. That was one way we could describe a linear function, is the outputs change at a constant rate, meaning they increase or decrease by the same amount each time. Same thing with exponential functions, except for exponential functions, over equal length input value intervals, the output values change proportionately. This is a fancier way of saying that it's multiplied or even divided by the same number. When we describe that multiplication factor, we are only going to put it as like times a number. So if you are dividing it by 2, we are going to say times 1/2 in this class for exponential functions. All right, the change for linear functions, that slope in your y values is based on addition, right? You're adding a number each time. And then for exponential functions, the change, which is your b, or in a geometric sequence is your common ratio. That would be a common difference for an arithmetic sequence. But your change in your y values for an exponential is based on multiplication. And then if you have 2 points, you can write the equation of a linear function, exponential function, arithmetic, or geometric sequence. So we saw that in lesson 2.1, where we were given 2 points of a sequence, and you could write the equation, the general equation for that. You've had tons of experience with that. And then if you have 2 points for a linear function or even an exponential function, we could use the regression lines from Desmos way back when in 1.14 to find our line of best fit that runs through both points. So here is a linear function table. So let's take a look at what these look like. So here, this linear function, our y's are increasing by the same amount, right? That's a jump of 1. And so that's our x's. Our y's, though, however, are increasing by a jump of 3, plus 3, plus 3's going down. And so what we can notice here is over equally spaced inputs, the outputs, your y's, have a constant first difference of plus 3. That is the best way to describe a linear function. Let's talk about the first difference, which is what this is. Or you could say the outputs have a constant rate of change of 3. So that's another way to describe linear functions. Both are equally correct because they are synonymous. For a quadratic function, right, if we were to ever ask about it, here, over equally spaced inputs, which is the same, the output values have a constant second difference of plus 1. So let's take a look. Our first difference, are those. However, those are not the same number. So sometimes for quadratic, we got to look at the second difference. And so this is going to be plus 1. From 4 to 5 is plus 1. From 5 to 6 is plus 1. And so here, this is our second difference. And so over equally spaced inputs, I always like starting with that statement. The outputs have a constant second difference of plus 1. That's an example of a quadratic. For an exponential function, over equally spaced inputs, and so now we're adding a new type into the mix. The output values change proportionately by a factor of 2. So here, our rule, we're not adding or subtracting the same number or even having a constant second difference. We are multiplying by a number. And these are pretty easy to spot just because you see them growing or getting bigger much faster than they normally would with an arithmetic or even a quadratic function. And so if we take a look here, right, you're jumping from 2 to 4, and then you're going from like 16 to 32. That's a much bigger jump. And so over equally spaced inputs, I always like starting with that, and then saying your outputs change, and here's the key word that I would be looking for, proportionately. So if you have to describe an exponential function on like a short answer question, that is the word I want to see, proportionately, and then I want to see what the factor is. So by a factor of, and then whatever number you're multiplying by. So this is very important because if it was, let's say your y values were 8, 4, 2, 1, and then 1/2, and you were dividing by 2, your factor here would be 1/2, not 2. Right? So it would, for this one, if those were your like y values here, you would want to say over equally spaced inputs, your output values change proportionately by a factor of 1/2. All right, so for example 1, pause the video now and try this one on your own, but you just want to identify if the function could be linear, exponential, or neither, and then identify your slope, which is like your m in a linear line, or your ratio, which is your b value, if it exists. So here, if we take a look, I see these numbers are kind of around the same range, so I'm going to go see if there's a subtraction rule, and there is. And so here, this is linear, and then our m should be -2 in this case, because that is our slope. Let's see, for this next one, add 1, add 5, or sorry, add 3, geez, add 5 here, add 7. So I noticed that it's not linear, but however, let's see if it's exponential. So here, if you go from 0 to 1, there's actually no number you can multiply by 0 to get 1, right? Because anything times 0 is 0. So this would fall under neither. This would actually be an example of a quadratic function that has a constant second difference of plus 2. But the question's not asking about that, so this would just be neither in this case. This one here, I see this one's kind of easy to spot, right? This should be exponential. And then here, our b value should be 2. And this one here is also pretty easy to spot just because you're going from 80 to 5. And so we're dividing by 2, but I don't even want to write that. I want to write times 1/2. And so this would also be exponential with our b value being 1/2. So you could have fractional b values. That is 100% fine with these problems. All right, so this question kind of returns again. Here you're going to be given a table and you will be asked what function type best models this function, either linear, quadratic, or exponential, and then give a reason for your answer based on the output values and input values and refer to the table in your reasoning. So we want to refer to those exact points. So I'll show you exactly what I'm looking for. Here we can see that you're multiplying by 2. So either linear, quadratic, or exponential. This is going to be exponential, should be our answer there. And then our answer is going to be pretty simple. You always want to start by talking about the input values. So over equally spaced inputs. Then you want to talk about your output values and how they change. So that's the part 1. The output values change proportionately. So that's part 2 that I would be looking for. And then I want to know exactly how they are changing. So by a factor of 2, because that's the number you're multiplying by. So that's all 3 parts that you need to get full credit for this question. I cannot tell you how many times we did this for a linear, quadratic, or cubic function and how many people got this question wrong. All right, so try example 2 here, and I am about to go over the answer. So this, as you can see, is times 1/2 times 1/2. If you're good with decimals, you should know that this is also times 1/2, and then that's a half of 7.5. So this should be exponential. All you got to do is just write that word, no explanation needed for part 1. For part 2, you would say over equally spaced inputs, the output values change proportionately by a factor of 1/2. And that would be a perfect answer for example number 2. All right, we got 3 more, so let's try all of these. And so this is going to be, I see this is plus 14. I see this is plus 14, plus 14, plus 14. However, a lot of people see 7, 21, 35 and go, oh, this is times 3. However, when we do 21 times 3, we should get 63, but we get 35. So we know it's not going to be exponential just from that. So this should not be exponential. That would be wrong if you put that. You should put linear. And then over equally spaced inputs, the output values have a constant first difference of plus 14, and that should be enough for your answer there. Taking a look at example number 4, here you're going from, I'm just going to rewrite the y values up here so we can have a little bit more room to work. This should be minus 5, minus 3, minus 1, plus 1. So here I'm probably going to go with quadratic, but let's just make sure. So plus 2, plus 2, plus 2. So this would be quadratic. And then over equally spaced inputs, the output values have a constant second difference of plus 2. And that should be good for example 4. For example 5, I see this is times 1/2. This is also times 1/2. This times 1/2 would give you 15 over 4 times 1/2, 15 over 8. So this is going to be another example of an exponential function. And then I would say over equally spaced inputs, the output values change proportionately by a factor of 1/2 there. All right. Now the next thing that is important is domain. And so remember, the domain of a sequence will not be the same as the domain of a function. The domain of a sequence here should just be discrete points or whole numbers. Because remember, you can only plug in 1, 2, 3, 4, 5, and so on into a sequence, right? You can't have a third and a half term. That doesn't exist in the context of a sequence, but you can plug in 3.5 into an exponential function. So the domain of f of x here, right, when it's just an exponential equation, should be all real numbers, or you could write from negative infinity to infinity if you want interval notation as well. So just know that those two are a little bit different. All right, so let's go back to the arithmetic and geometric sequences and get a little bit more practice with this. This is going to be just using story problems with this. So some of these you'll need a calculator for, some you may not. These two you shouldn't need a calculator for today, hopefully. And so this section also reviews how to find future terms in an arithmetic or geometric sequence. So remember, just set up both terms. If you're given two terms, to find your common difference or common ratio. Then set up an equation to find a general equation for a of n or g of n, and then find the term you're looking for using the general equation. So that's probably what most of these story problems are going to do. They won't give you the common difference or common ratio. They will just give you two terms and ask you to find a third one. So let's take a look here. A large theater has a row of seats where it's modeled by an arithmetic, so it will tell you what sequence it is modeled by. If the fifth row has 31 seats and the 11th row has 49, how many are there in the 25th row is what we're looking for. So here, set up our equation, a of n equals a of k plus d n minus k. And now this is going to be set to our a of n, and this will be set to our a of k, because a of n should be our term that comes later. So our 11th term comes later than our 5th term. Plugging it in, 49 equals 31 plus d, which is what we're solving for. And then here, n should be 11 minus k, which should be 5, and just solve. Minus 31 from both sides, and divide both sides by 6. You should get your common difference to be 3. Now we can plug this into our general equation. So a of n equals, and we'll use a of k again and repeat it. So 31 plus 3, our common difference, n minus k, which is 5 in this case, And now a of 25, just plug 25 in. Make sure you do your order of operations correctly. And you should get 91 to be your 25th term, which means that's how many seats there will be in row 25 there. All right, and then finally, example number 8. Here, we are going to use a geometric sequence where 2 people have heard the rumor on day 3, and 8 people have heard the rumor on day 5. How many people have heard the rumor on day 10? And so setting up our geometric sequence, g of n equals g of k times r n minus k. This is going to be our g of n. This will be our g of k. So 8 equals 2 times r to the power of 5 minus 3. 8 equals 2r squared. 4 equals r squared. R should equal plus or minus 2, but really r is just going to be 2 because typically with story problems, a negative common ratio does not make sense in the context of the story. So here, we're going to ditch that solution, and so r is just going to be 2 here. Then g of n equals, we'll reuse g of k, so 2 times r, which is in this case 2, so we can sub that in, to the power of n minus 3, and then g of 10 equals 2 times 2, 10 minus 3, 2 to the 7th, and then this should be 256. I would give you a calculator for that, and that should be example number 8. If you guys have any questions, please come see me in office hours, and I will see you guys later. Peace.